Hi everyone, welcome back to One Dimensional Kinematics, The Adventures of Jim and Cindy, and this time we'll be talking about position versus time graphs with speed and velocity.
Okay, conceptual example number 4. Cindy decides to go to a cow racing competition with Jim. Rank the cows from fastest to slowest. So we see this is a position over time graph, and we have these 4 cows here. And we want to know which ones are the fastest and which ones are the slowest. Fastest to slowest. So when we're trying to do this problem, how we're trying to find which one is going to be the fastest is we want to be looking for which slope is the steepest. And we can see that Elsie here has the steepest slope. And why this shows that it's the fastest is this is showing that it has the shortest amount of time. In the shortest amount of time, it's gaining a large amount of ground. So it's gaining all this ground in this short amount of time. So whenever it's able to gain a large amount of position over a short period of time, that means that it's going really fast. So Elsie is going the fastest here. And then when we look over here, what we can see is what's going to be next is Bessie. Bessie has the second largest slope. And so she is going to go the second fastest. And then we see Dolly here. Dolly over here has the third largest slope. So Dolly. And then lastly, Moolinda. Moolinda has the most shallow slope. And again, I want to emphasize, so Moolinda goes from this position to around this position, but it takes her this long in order for her to get to there. So we know it's really slow. But when we compare it to Elsie, she goes from here all the way to over here in a very short period of time. So since it's the period of time is shorter and the distance is greater, we know it's going a lot faster than Moolinda. So the slope of a position versus time graph will show how fast it's going. Alright, conceptual example number 5. Harry and Jim decide to go kayaking together during their Thanksgiving break. At what times are Harry and Jim in the same place? So we're going to look at this. This again a position versus time graph, and we want to know at what time are they at the same place. So graphs may be scary, but you just want to take your time to just think about it. So we want to know at what time are they at the same place. So we're just going to look over here, and we can see over here at this time here they are at the same position, which is 6 kilometers. So at this place right here, they're at this time right here, they're at the same position, and we can see that is at time 1 hour. Okay, so that is at time 1 hour. So at 1 hour, they're both at 6 kilometers. So we can say 1 hour. How much time does Harry spend on the river before he passes Jim? So we can see this one here is Harry. And we can see that Harry, well, how much time does Harry spend on the river before he passes Jim? So Harry is always kind of behind Jim, but at this point right here, this is when he starts to get ahead of him. Okay, this is when he starts to get ahead of him, and after this point, he's always ahead of him. So again, it's going to be at the 1 hour point. Where on the river does it appear that there might be a swift current? So we're going to be looking at this, and what we want to see where there's a swift current is when they're going to start to go faster. So we can see that this is pretty linear over here and linear here, and this is also linear, but we see that it has the steepest slope right here. It goes from going like this to starts going dramatically more steep over here. So what this means is there's something that's making them both go faster. And what we can imagine, if something is making them go faster, it might be the swift current that they're talking about. So we can see where on the river does it appear. So we can say it's going from like the 6 kilometer mark to over here, the 9 kilometer mark. So I'm going to say 6 kilometers to 9 kilometers. because they both get faster during that position. Okay. All right. So, example 13, let's just start doing some math here. Jim is training for another race and he decides to use an app to track his runs. How fast did Jim run in each of the intervals? So this is again a position versus time graph. This is the first interval, second interval, and third interval. So how fast did Jim run each interval? So let's look at number 1. So this may be a little bit complex to see, but what we can see is that Jim, during this time, we're going to call this time 0, and this is going to be 4 seconds. So from 0 to 4 seconds, he goes from position 0 meters to position 20 meters. So we can see that the first interval, the time it takes is equal to 4 seconds. And the first interval, he travels also a distance of 20 meters. So distance equals 20 meters, time equals 4 seconds, and now what we can do is we can find the speed. Speed is equal to distance over time, which gives us 20 divided by 4, which is equal to 5 meters per second. So what you're going to notice is this is what we can do. We can find the variables from this graph and find what the speed is, or what we could do is this speed equal distance over time is the same as the slope, the rise over the run. The rise being the distance, the run being the time here. Okay, so the slope gives us the speed. So for the second one, the second interval, what we see is, okay, it's going to be taking him 4, 6, 8, 10. So it's going to be taking him a total of 6 seconds. Time equals 6 seconds. And the distance he travels is he goes from 20 meters to 20 meters. So actually he doesn't travel any distance. He stays the same. So distance is equal to 0 meters. Again, speed is equal to distance over time. And we get that his speed for the second interval is 0 meters per second. He probably just got tired and we're just taking a break. Also, if we just look at the slope, there is no slope, so we can see that his speed is 0 meters per second. Lastly, for the third interval here, let's see how much time takes place. So we're going from 10 to the middle of this, so that's going to be 10 to 13, so this is 3 seconds. And the distance traveled goes from 20 to 40. So the total distance traveled is going to be equal to 20 meters. Now again, we're doing speed equals d over t. Doing the slope, 20 divided by 3, which is equal to 6.67 meters per second. Okay, so he goes out with an all-out sprint at the end. What was his average velocity? So again, the average velocity is equal to the total displacement divided by the total time. That being said, the total displacement is from here to here, so that's going to be 40 meters. And the total time is from 0 to 13 seconds. This is going to give us 3.08 meters per second. Okay. Dun, dun, dun. All right, so let's continue this. Let's see if we get the hang of this. Jim continues his workout, continue to find his average velocity for each segment. All right, so let's look at number 4. So number 4, now that I showed you how to do this, I'm just going to pretty much be using this slope. Number 4, the distance the time it takes is 4 seconds, goes from 0 to 4. The distance, it goes from 0 to 5 meters. And now we're just finding the speed is equal to the distance, 5 meters, divided by the time, 4 seconds. And we get this is equal to 1.25 meters per second. The fifth interval. So again, there is no slope over here. He stays at 5 meters, he ends at 5 meters, so there's no slope, meaning this is going to be 0 meters per second. 6. So what's going on here? Going from 5 meters all the way down to negative 30 over here. And it takes him 8 to 12, so 4 seconds. So let's just kind of do this out. So this is asking for the average velocity. So this is important because it's not just talking about the distance anymore. We're looking for the velocity. So velocity is equal to the displacement over time. That being said, I'm going to simplify this displacement further, which is equal to the final position minus the initial position over time. So we know the final position over here is negative 30 minus the initial position over here, which is 5. The time it takes goes from 8 to 12, so that is equal to 4 seconds. And then, let me put this in meters over here. And then we can find that this gives us 35, negative 35 divided by 4, which is negative 8.75 meters per second. What we can see is that he's starting to run back. And number 7, again, there is no slope. He's staying at that negative 30. Probably after that long sprint, he's just resting here. So we can see that this is 0 meters per second. There is no slope. Okay. Now, we're going to be doing some drawing the graphs for ourselves. So I'm going to read a little story, and then we're going to try to graph this all out. So a man's journey with his dog. A man slowly walks out of his house with his dog for 4 seconds. The dog stops to use the bathroom next to the fire hydrant and does his business for another 6 seconds. Soon after, the dog sees a squirrel and sprints after it. The man sprints after the dog for the next 2 seconds. The man stops the dog and scolds him for 2 seconds. After getting strange looks from everyone, he realizes that he doesn't have a dog. So he starts to jog back home with his jump rope. This takes him 4 seconds. Okay, very interesting story. Let's see if we could draw this out. So what we have is a man slowly walks out with his dog for 4 seconds. So he's going to be going slow. So we're going to draw something like a shallow slope like this. Okay? And maybe I'll use the second part is the dog stops to use the bathroom next to the fire hydrant and does his business for another 6 seconds. So the dog isn't moving. So what we see for another 6 seconds is it's going to not be moving. It's peeing. And it's just going to be a flat curve because it's going to be staying at the same position. Soon after, the dog sees a squirrel and sprints after it. The man sprints after the dog for the next 2 seconds. So it's going to be sprinting for 2 seconds. So it's going to look something like this. Okay, it's sprinting for 2 seconds. The man stops the dog and scolds him for another 2 seconds. Okay, scolding the dog for another 2 seconds. So again, it's going to look like this. It should be flat. After getting strange looks from everyone, he realizes that he doesn't have a dog. So he starts to jog back home with his jump rope. This takes him 4 seconds. Okay, so he goes back home, meaning he has to go back to where he started in 4 seconds. Sorry, this isn't, I kind of drew this wrong, but it's like, it's going to go all the way over, going back home, which is at the 0 meter mark. Okay, it's going back home. It's going to take him 4 seconds to get there, to go back home to the 0 meter mark. Alright, so let's try this one again. So we have an ant slowly sneaks up into a grasshopper's hut and finds his way to the central office in 6 seconds. So he slowly gets there. A giant grasshopper spots the ant and chases the ant out of the hut. The grasshopper continues to chase him out into the wilderness, which takes a total of 4 seconds. The grasshopper catches the ant and leaves him buried in the ground forever. Okay, so let's look at this. An ant slowly goes into the central office of the grasshopper. So it's going to be slow, so it's sneaking into that office. It's going to look something like that, okay? So shallow, slow. A giant grasshopper spots the ant. The grasshopper continues to chase him out into the wilderness, which takes a total of 4 seconds. So it's going to be chasing him out. So if it's chasing him out, what that means is it's going to look like this is where he started, and it's going to continue chasing him out for 4 seconds. So it's going to look something like that. Last one, the grasshopper catches the ant and leaves him buried in the ground forever. So what's going to happen is going to leave the ant in the ground, means not moving. It's going to be staying in this position forever. Alright. Alright, so let's go to example 17. Back with Jim and Cindy. So, Jim walked 10 meters down the school hallway from the cafeteria to the band room. Cindy, who has developed an interest in Jim, oh interesting, records his position every 2 seconds and notice that he moved 2.6 meters every 2 seconds. Wow, she's really seeing everything he does. At what time was Jim in the following positions 3 meters from the cafeteria? Okay, so we have a little bit of data here. We can see what we know is Jim Jim walked 10 meters down the school hallway from the cafeteria to the band room. Alright, so let me just draw this out. Cafeteria. And then this is the band room. And this is 10 meters. Okay. At what time was Jim in the following position? 3 meters from the cafeteria. Okay. So we know, let's see. Let's first find what the speed of Jim is. So we know that Jim distance is equal to 2.6 meters. And for him to move 2.6 meters, it takes him 2 seconds. Okay, so we can find his speed, which is equal to 2.6 divided by 2, which is equal to 1.3 meters per second. So what we want to find out is at what time was Jim in the following place 3 meters from the cafeteria. So we want to find out 3 meters, and we want to find out how long it takes him to travel these 3 meters, the time. So what we know is, we know his speed is equal to 1.3 meters per second. We know we want to find out the time it takes him to travel 3 meters, so the distance is equal to 3 meters, and we want to find out how long that takes. We put it into the formula. Speed is equal to distance divided by time, and we find that 1.3 meters per second is equal to the distance, 3 meters, divided by the time. Do a little bit of algebra, and we find 3 divided by 1.3 is equal to 2.31 seconds. So in 2.31 seconds, he is at this 3 meter mark from the cafeteria. At what time was Jim in the following positions? 3 meters from the band room. So we want to know 3 meters from the band room, which is going to be 7 meters here. We want to know the time. Same kind of thing we're going to be doing here. We know his speed is equal to 1.3 meters per second. The distance he travels is equal to 7 meters. And now we're looking for the time. Again, we use the same formula. Speed is equal to distance over time. And we get 1.3 meters per second is equal to 7 meters divided by the time. The time is going to be 7 divided by 1.3 which is equal to 5.38 meters, 5.38 seconds. But the real question is, what did he get at the cafeteria? So Cindy sees him buying a hot dog at the cafeteria. Jim must really like those hot dogs over there.